Good morning and welcome you all to this session of the course Conduction and Convection Heat Transfer. Last class we were discussing the Fourier laws of heat conduction, which defines the heat flux is proportional to the temperature gradient, and the proportionality constant is called as or defined as thermal conductivity, which is a property of the system. Now in this regard, again I repeat that the two modes of heat transfer, conduction and convection, is this way, that conduction is the basic mode of heat transfer, and when there is a flow in a medium which is present in liquids and gases, then this conduction mode is affected by the flow and we call it as a convection mode. So therefore, convection mode cannot appear in solid. The heat transported in the solid is always by conduction mode purely without being affected by flow, because there is no flow within the solid. Solid as a whole can be translated, but solid within the solid there is no flow. And under some special conditions, when the fluid, the liquid or gases are stationary, there is no flow, then the heat transfer takes place purely by conduction. And when we will talk about conduction heat transfer, we will consider purely conduction mode without being affected by any flow. That means there is no flow in the medium, which mostly happens in solid. And if we now think that the heat conduction again, then we have seen that the heat flux, that is the heat transfer per unit area normal to the direction of heat transfer, is minus k gradient of grad T, where the heat flux is taken as a vector. Now therefore there has to be a temperature variations in the space coordinates. It is a continuous temperature variations for which we can define the gradients. That means in the medium, the temperature has to be a function of space coordinates. If you consider a Cartesian coordinate system x, y, z, simple, that T is mathematically expressed as a function of space coordinates x, y, z, and also it can vary with time. That means at any point the temperature can also vary with time. That means temperature is varying with the space coordinates, so there is a temperature distribution, and this distribution is also varying with time. That means a function of time. So in general, one can express temperature in a medium of heat conduction or in any medium, but here now we are discussing the heat conduction. In a medium of heat conduction is a function of x, y, z space coordinate and time. Now in this regard, we should think of two states, that one is steady state heat transfer and is one dimensional, two dimensional or three dimensional heat transfer. Now in steady state heat transfer, as you know, the word steady is associated with invariance with time. That means something which does not change with time. For example, you know the steady flow, where the flow velocity, pressure, these quantities and the derived quantities like mass flow rate, volume flow rate are all invariant with time. So for a system at steady state, we know the properties are invariant with time, except for the control mass system, which is defined as a fixed quantity of specified mass. Mass is excluded, other properties are invariant with time, because mass is always invariant with time. So we don't bring mass. So even at unsteady condition, mass is constant. But for a control volume system or control volume inclusive of mass, everything should be constant with time. That means all parameters, all properties will be constant with time. So therefore temperature being a parameter, temperature is, or a property of a system remains constant with time under steady state situation. And we are concerned with the heat transfer processes at the moment. So therefore, when the temperature ceases to be a function of time under all steady state situations, we call it at steady state. That means in that case, temperature becomes a function of space coordinates. That means that at steady state heat transfer, temperature is a function of space coordinates only. That means if we get a temperature distributions within a medium, that remains invariant with time. Now when temperature is a function of 3 space coordinates, the heat flux in all these space coordinates exists because of the respective temperature gradient. And this heat transfer situation is known as 3-dimensional. If this is not a function of time, then it is a steady state 3-dimensional heat transfer process. Similarly, if the temperature becomes a function of only 2 coordinate system, ceases to be a function of z, then it is a 2-dimensional, or any 2 x, z, depending upon the way you define your coordinate axis. And if the temperature is a function of only 1 space coordinates, that means temperature varies only in one direction. So heat flux exists in that direction only. That is a 1-dimensional heat transfer. That means Qx only Qx exists. Only Qx exists. That is 1-dimensional steady state heat transfer. Heat transfer. So this is the mathematical definition of steady state heat transfer, 1-dimensional, 2-dimensional or 3-dimensional heat transfer. Let us concentrate on 1-dimensional steady state heat transfer, where temperature ceases to be function of time and it is a function of only 1 space coordinates along which there is a heat flux. So to realize this in practice, let us consider a wall like this. Let us consider a wall like this, whose dimension in this direction, which we call length or width, is much small, L, compared to its dimension in this and this direction. That means if you consider this to be x, this direction to be y, and this to be z, that means its dimension in y direction, which you can call height, its dimension in z direction, which you can call as the breadth or whatever maybe, is much higher as compared to its width or length L. If you consider such a situation of a wall or a slab which has a constant cross-sectional area with respect to the axis x, that means the plane wall of this dimension, this is known as plane wall. Plane wall. And if we consider a situation that the left-hand surface is kept at a temperature T1 constant, the surface temperature is constant. That means at each and every point on this surface the temperature is T1. That means which is independent of y and z direction. And if this right-hand surface is kept at a constant temperature T2, this we assume, this is the prescription of the problem. That means problem is specified like this, T2. And if T1 is greater than T2, by our basic definition of heat transfer, heat will flow in this direction from high temperature to low temperature. Now, this case, assumes a one-dimensional heat transfer. Why? Because temperature varies only in the x direction. It is by intuition the temperature at any point will be a function of x only, because in y and z they are constant. The boundaries are such, the boundary conditions have been made such that the problem is made one-dimensional because of the boundary condition and the geometry. The temperatures are constant, two phases, and moreover this dimension, the length or width, is much smaller compared to the dimensions in other direction. So by the definition of the problem, by its geometry and boundary conditions, it is one-dimensional. Now, how to conceive of a steady state? Now, by basic understanding of the steady state, all points the temperature has to be invariant with time. There may be a distribution, but invariant with time. So to meet up that, we have to have two physical requirements. One is that definitely the boundary temperatures has to be invariant with time, which I have prescribed for this problem. And at the same time, there should not be any energy generation internally by this wall, by any action. By any action, there may be an internal reaction or anything else. At the same time, there should not be a heat absorption by any action within the wall. And wall should allow the heat to flow without interruptions. That means without adding anything to it or without taking anything from it, which means that the heat flows at any section will be constant. And as a whole, I can tell the amount of heat which is coming in to this wall from the left side is going out from the wall at the right side, the same heat. Now, if I take a section at x and let the cross-sectional area is Ax, then what is the heat flux? Qx is minus k dt dx. Now, t is a function of x. So, therefore, dt dx can be either a function of x or constant. It can never be a function of y or z, which means that Qx is not a function of y or z, provided k is independent of the directions. Well, then we can tell that heat flux is constant at all points on this area, so that I can write Qx is equal to minus k Ax dt dx. And if this is constant at all planes because of the requirement of the steady state, then one can write that this is equal to constant. This is equal to constant. That means simply k Ax dt dx is constant, and that is the requirement of a steady state one-dimensional heat conduction. Now, if we assume additionally that k is independent of the temperature and the direction, that means the material is isotropic and its thermal conductivity is independent of the temperature or doesn't vary much within this range of temperature studied, then at the same time, if we consider Ax constant, consider means the problem is defined for a plane wall. That means the cross-sectional area Ax is independent of the direction of heat flow x. In that case, we can write dt dx is equal to constant. That means we get a linear temperature profile from T1 to T2 within the slab. So therefore, a steady state heat transfer with constant thermal conductivity, with constant cross-sectional area, which happens in a plane wall, the temperature gradient is constant. That means the temperature is a linear function. This you can also do it in this fashion in a little elaborate way. I think that will help you afterwards in the deduction, that you can do in this way. In a separate diagram I am showing you that if you take a small elemental volume or small element within the wall which is kept here as T1 and it is temperature T2, and at x, at a distance x, I take a small element of length delta x, then we can, it is a little elaborate way. This is the most simple way of looking into it, that if the total heat flux at this left side of this elemental volume is Qx, and if I designate the heat out from the right face at x plus delta x as Qx plus delta x, then I can write the same thing just in a different way. Qx in a little elaborate way is nothing but minus Kax, because dt dx is not a function of y, t is a function of x. So therefore the same logic, and Qx plus delta x we can expand in a Taylor series at x in the neighborhood of x plus delta x by this way, ddx of Qx delta x plus higher order terms in delta x, higher order terms in delta x. That means next term will be double derivative delta x square by 2, as you know, plus going on. And if delta x is very small, in the limit delta x tends to 0, in the limit delta x tends to 0, always we do that, neglect the higher order terms. And therefore, Qx plus del x is Qx. That means plus d, that means this can be written as, with the help of this, Kax dt dx plus ddx minus Kax dt dx into delta x. Here I have not taken into consideration that k is constant, ax is constant. This come as a whole within the bracket ddx. That means this can change with x. Now, if it has to be at steady state, there should not be any generation of energy within the element, or there should not be any absorption of thermal energy within the element. That means the element will act as a transparent element. Whatever it receives, it will allow to go out. That means a steady state control volume. Influx of any material, whether it is mass or energy, equals to the a flux. So therefore, one can write Qx minus Qx plus del x equal to 0. And if you make this thing, you arrive at this same equation, that this is constant. Means ddx, this minus this means ddx of Kax dt dx del x is 0. So therefore, we get the same result, that Kax dt dx is constant, is not dependent on x. So if you make this, you get the result that ddx of Kax dt dx into del x is 0, which means that Kax dt dx is constant. Okay? So, therefore, the requirement for a steady one-dimensional flow is this, and if Ax is constant, if it is a plane wall, then dt dx is constant. So, therefore, for a plane wall with constant thermal conductivity, we have a temperature. If you show the temperature scale here, this is T1 and this is T2 from any reference datum. So, we give a linear profile, the slope of which will depend upon the thermal conductivity. Okay? This is clear when we have a linear temperature profile. Now, in this context, I will tell you certain things. Okay, let me rub the board and now, if we have a solid like this whose area is not constant, and if we try to conceive a one-dimensional steady state heat transfer by making this surface at a temperature T1, this is at a temperature T2, so that T1 is greater than T2, then what will be the temperature variation? Will it be linear? Will it be linear? Will the temperature variation at steady state, one dimensional, will it be linear? No, because area is not constant. But one catch is here, that this type of geometry, which is not a plane wall, that the area is not constant, strictly speaking, doesn't give a one-dimensional heat transfer picture. Usually, this type of geometry, the temperature is a function of both x and y. But under certain cases, the variation across this section is less as compared to the variation along the length, depending upon the boundary conditions. So, what we do, we take almost an cross-sectional average temperature T and tell it as a function of x. This is cross-sectional average temperature. That means it is, in other words, visualization of a really, truly speaking, two-dimensional heat conduction as one-dimensional, when the variation in other direction is small. So, this happens in this type of geometry. Purely, strictly speaking, a one-dimensional heat conduction happens in a plane area flow. This I will connect afterwards after the derivation of general heat conduction equation. So, in this case, I know my basic Kax equation for steady state is dt dx constant, not dt dx constant. Now, if k is constant, that we will assume here Ax dt dx is constant. That means dt dx is inversely proportional to A. So, such a diverging medium, a bar like this, a conical bar. So, that means temperature variation will be like this. This is T1, sorry, this will go like this. So, this is T2. That means the slope goes on decreasing. It is just the reverse if this is a converging bar. So, this is clear. So, therefore, the essence is that Kax dt dx is constant for one-dimensional steady-state heat transfer. K may vary, A may vary. K may be a function of temperature. Since T is a function of x, so K varies with temperature, it will be also function of x. A may be a function of x. So therefore, to find out analytically the temperature as a function of x, this all depends now on mathematics. So concept of heat transfer ends here. K dt dx is constant. Now rest is mathematics. A very simple, or the simplest case is that K constant, A constant, plane wall, then the mathematics becomes probably the simplest thing, that dt dx is constant and a linear temperature profile. Okay.